That was the most bizarre thing. So we've been looking at hydronium ions and hydroxide ions in solutions, and we've been saying one's an acid, one's a base, one's a conjugate acid, one's a conjugate base, okay? Now we're going to start looking in terms of the titration curves or pH curves. They're the same thing, they're interchangeable. You can't do one without the other. When we look at an acid-base solution, a weak base sample is titrated with a strong acid titrant. So let's refresh our brains. Here's our burette. Here's our Erlenmeyer flask with our sample in it. Okay?
Titration, that's what you have to do to a very small amount.
Yeah. So where does my titrant go and where does my sample go?
Your titrant goes in the burette.
Right. So my strong acid, or whatever it said, strong acid titrant, and this is going to be my sample in here. Okay? So remember, for this to work, we need lots of weak base or acid, and we need a little amount of strong base or acid. Okay? When we look at acid-base titrations, the titrant continues to be added well past the end point. Okay? So the end point is when we see the very first color change that stays. Remember when we tried to do the phenolphthalein challenge and who could get it to go to the faint pink versus the brilliant pink? Okay? The faint pink that stays is the end point. That's where we've flipped over. The bright pink means that we've got more base or more acid. Okay? And so when we do that, we measure the pH at the same time that we measure the volume of the titrant going into the sample. And we do a relationship between them. And we call it a titration curve or a pH curve. Either or. The pH is the responding, the amount of titrant that we add is the manipulated. Okay? An indicator is used to observe the endpoint. So again, last year, we worked on this very last page here, and we had all these different indicators, and they had pH ranges. And in there, so if we were looking at bromocresol green, and it's going to go, if we started with a base, it would start out blue. As we added our acid, it would flip over to yellow. The end point is when it goes, what's the color between yellow and blue? Green. So when the solution would go green, that's the end point. You remember that piece? Is it all coming back as a haunted memory?
Hold on, just as a recap. Undersaturated would be if it would be still.
We don't use undersaturated or oversaturated here. Mm-mm. Mm-mm. Okay. So it says acid-base indicators are weak acids. They're designed to minimally impact the titration. Okay? They'll have a small ionization constant, but it doesn't really super harm the titration. The indicator acid is one color, and the conjugate base is another color. Okay? So if I was looking at this piece here, and bromocresol green, my acid would be yellow and my conjugate base would be blue. And at the flip over point, the end point, it would be green. Okay? And they write it like this here too. Bromocresol green is H B and then a G for green. And then the base is B negative because this acid donated the proton, right? That's the definition of an acid, is it donates the proton, it donates the hydrogen. The base accepts the proton. And we don't always, the reason we say proton and not hydrogen is because what binds with hydroxides? Sodium, potassium, lithium to make bases. So it's not always a hydrogen. Okay? All right. So let's look at phenol red. So everybody open up their data booklets to this very, like, not back page, but that back inside page. So phenol red is, I was doing jewelry and I did not have my glasses, so everything is blurry. Phenol red is near the bottom, and as an acid, it's written as HP, I just saw it, HPR, okay? That's our acid. We're going to add it to water, and it's going to produce PR negative, thank you, and H3O plus. Okay, and so this is our weak acid indicator. This is our weak acid indicator, is the phenol red. And when we get all the way over to base, the solution will be red, right? When we look at phenol red, here's our acid, and it's 6.6, so it's barely acidic. But when it flips over to the base, the conjugate base, it's going to be red.
Wouldn't you think that red would be acidic and yellow would be more base?
Colors have nothing to do with it. Okay? I mean, Avery would love to have that conversation with you about colors, but okay. So let's predict which way the equilibrium will shift when a strong base is added to a phenol red indicator. So remember our things when we looked at Le Chatelier's principle? What's changing? Our H3O plus is going to decrease when we add a strong base, right?
So why do you add a plus there?
Number one, step number one. What will the system try to do? System will try to increase
Oh, that's a down arrow. I thought that was
H3O plus, right? So then what will happen? Which way will it shift? The system's going to try and increase H3O plus. It'll shift right. So the products will be favored. Right? We have to look at what are we doing? If we're adding a strong base, we're reducing our acid. What will the system do to maintain equilibrium? And so what does that look like as an end result? This is all the same thing that we've used for Le Chatelier's principle. Okay? What observations would we see if we shifted to the right, if we favored, if we added more strong base? If I added more strong base, if I increased this, what would happen here? It'll just get more red. Okay? Okay, you'll get a more red solution.
that says more red.
Yeah. You're just supposed to know that there was an O there. Okay, let's look at this following titration curve. Let me draw it out for you. This is pH, 2, 4, 6, 8, 10, 12. And let's add some sample here. So this is 20, 40, I did it wrong. This is 40, sorry. 40, 60, 80, 100, 120. And this is mils of sodium hydroxide added. Okay, sodium hydroxide, acid or a base? It's a base. So chances are, what's in our Erlenmeyer flask? An acidic sample or a basic sample? An acidic sample. So let's say we start around a pH of 3. Okay? You just said it was an acidic sample.
Oh, sorry.
So we have no titrant added. This is titrant. Yeah, this is titrant. So we're starting out at a pH of 3. And I'm going to add some sodium hydroxide. And we're going to start to see, just make sure I get this right. I'm going to bake it out here. We're going to start to see some increases. Not radical increases, but you know that the pH is slowly changing. Okay? A little bit of increase. Then we hit the 100 mil mark, and we're here. And then here. And then we're here. And then 120. We're here. We're here. And here.
And then at 200, you make a big jump again?
No, there's only one hydrogen. You're only going to have one jump. We're going to talk about that. That's a good question, Riley. Okay? So then we do this. It's the one time that you kind of get to play connect the dots. Okay? Because what have you always done your whole life with graphs? Line of best fit, right? This is the one time you're allowed to play with graphs. Now I'm going to teach you something. This is an old school trick. You get taught this in university. I'm going to teach you now because it makes a world of sense. How do I know where the middle point is? Where the end point is? I don't know because I did a drop. It was clear. I did a drop. It went faint pink. I did another drop and it went pink. That's literally how it goes when you work with phenolphthalein. That drop where I added it and it went to that faint pink, one drop is roughly the equivalent of 0.1 mils. So was it 0.01, 0.02, 0.03, 0.04, 0.05, blah, 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 0.09, or 0.1 that made the flip? We don't know. Somewhere within that drop made the change. In order to find the end point, we take this relatively flat part of the curve here and we draw a line. Okay? Yep. You can watch it till the end if you want. And then you take up here roughly the flat part. Okay? And then you take this line here and the majority of this line. So, I mean, you can have a line that goes like that. That's fine, as long as you have the majority of this line in here. And you simply measure it. Oh, look at that, 1 inch. So 1/2 inch, that is my endpoint. So then I would go across, if this was fancy graph paper and everything was straight and lickety split, you would go over this way and you would come down this way. And I would say that at pH 8.7 and 100 mils was my endpoint.
So that's basically the coordinate for your endpoint then?
Well, I wrote it backwards. I wrote Y and then X.
It doesn't matter. It's just
Yeah, well, we don't take coordinates off this graph.
because you're saying pH.
Yeah. So this point here is my equivalence point. Okay? This region here, the other day, we talked about a buffer, right? Where you add and add and add and add and nothing happens, nothing happens, nothing happens, and then you add again and everything changes. And then this levels off. Now, is this a buffer region? Or is it the end of the titration? Well, I'm adding sodium hydroxide. So what's my pH going to do? It's just going to get more and more basic. So this is not a buffer region. Okay?
Buffer region would be if it's acidic.
This is just titrant being added and in excess. Okay? Yep. Yep. Okay. So this graph gives us a whole bunch of information. Okay. The sample type was a what? If my titrant is a strong base, a weak acid. Okay. My titrant type, it tells us sodium hydroxide. What is that? Strong base. My equivalence point, which is the midway point between the starting of the titration and the end of the titration, it's the end point, is roughly at, yep, 9, 8.7, however you want to do it. Okay? Okay, then you would have filled in 7.7. Okay? It's however you drew your line. Chances are, if you're adding a base, it's going to be higher than neutral, but that's okay, Declan. It's just how you freehand drew your graph. Okay? My indicator selection, what do you think they used for an indicator? We started at a pH of 3, and we went up to a pH of, looks like 13, 12. Let's see. You would say what? Methyl orange starts at 3.2 and it's over by 4.4. We flipped at 9. So we got to start low, or we have to have something that has a color change around 9. So here, let's look. We have 8 to 9.6. Halfway would be 8.8. So it could be potentially thymol blue, right? Because it would have started below 8, it would have been yellow. At the flip point, it would have been green. And then as we added more base, it would have gone blue. Could have used thymol blue. Could it what, Riley?
You have used the 8.2 to 10.
This one here? What's that word? Take a chance. Phenolphthalein. So it's going to flip. This is what? 1.8. So 0.9. It's going to flip at 9.1. So this one would work. It would be a very faint pink. This one is over 9 already. These are over 9. These are over 9. So we could have picked thymo blue or phenolphthalein. So I'm going to tell you in here that we used phenolphthalein, and I'm going to tell you why. Nope. The reason we use phenolphthalein over thymo blue is cost. Phenolphthalein is cheaper than thymo blue. Yep. Yeah, we've used a bunch of different ones. Yep. Phenolphthalein is just cheaper to use, easier to make. Nope. Exactly. You know what, Declan, in industry where I worked, they also used phenolphthalein because they had test kits in little bottles, and it's cheaper to buy phenolphthalein from a supplier than it is to buy thymo blue. Nothing wrong with thymo blue. Got nothing against it. It's just more expensive. Yeah. Now my buffer region. Where is my buffer region? So we started at a pH of 3 to about a pH of, let's say, 4.2. Okay, your graph might look a little bit different, but it's this region in here before it starts to take off.
So once it leaves that kind of...
Once you start to see a radical change in your pH, like, so you are going to honestly do a drop, and it's not going to happen, it's not going to happen, it's not going to happen. You measure every half a mil, and it goes 3.1, 3.1 and a half, 3.2, 3.2 and a half, 3.3, 3.3 and a half, 3.4 or 4, and then it goes 4.9, 6.8, 10.2. It happens like that. It's a radical change really quickly. Okay? And if you're in industry and you're being sassy and you're doing a quick titration and you miss your endpoint, you curse yourself out. Because you have to do it properly. But when you got 4 of them set up and you set them all by drip, and then all of a sudden one goes pink and you look over and you miss the volume. Just saying. Might have happened a time or two. Yeah, you want that in between. And you know what? In industry, Declan, we don't go for that faint pink. In all honesty, I don't have time. When I've got a client sitting out on a lease wanting to know if they can deal with their flooded lease, they just want to know, is it good to go? That's what they want. Alberta Energy and Utilities Board wants an actual number. So I just do a rapid test, and I'm just looking for when it goes pink, when I've got definite color change. Because what's the difference between one drop, it's faint pink, and one drop, it's pink? It's a difference of 0.1 mil. And on a flooded lease, what's 0.1 mil, right? So in industry, now in research, they're absolutely going to go to that faint pink. But in the oil patch, we just go till we see pink. Or we go till we see blue, or we go till we see red. What? Yeah. So the indicator tells you when you go from your weak acid over into your conjugate base. Or vice versa. Sometimes we titrate down, we put base in the beaker and we put acid in the thing, and it tells you when you go from your base to your conjugate acid.
So what would be known
that end point is when you've made that conversion. Yep.
What would be known as
Okay. Polyprotic substances. Polyprotic meaning multiple, right? So phosphoric acid, H3PO4, borate or boric acid, H3BO4. Okay? They have multiple hydrogens to donate. And so what happens is you get multiple curves. You get a curve for every hydrogen that's donated. Yep. 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 Absolutely. Because you can donate that proton where you end up as a base, or you start out as the base. You start out as only having borate ion in your solution, and as you add your acid, you form boric acid and you go down and you, okay? So, yes, you can have more than one equivalence point. You'll have an equivalence point for each hydrogen. Okay? What does that look like? Here we go. I know, we're so close to being the official last lesson of Chem 30. This is the last lesson.
I just want to say, I don't know how to calm down. No, he told me at the golf course.
Okay, wait, I'll pause it. I'm going to start out with my sample here. So what do you think is in my beaker? You have two choices, acid or a base. Okay, it's in your beaker, in your Erlenmeyer flask. A weak base. Okay? Yeah, weak acid is 7 and down. Yeah. Okay? So here we go. We're plotting along. Here's my magic marker. So I'm going to do this. And I want to do this. Okay. Add all these points. And then I see this. And then I see this. And here. And then I see this. Okay, each one of those dots is a measured pH after a certain addition of acid being added. So this is pH. This is mils of 0.1 molar hydrochloric acid. Okay. What do we see about this region here?
Why do you have the 0.1 there, sorry?
What? Because it's just telling you the concentration of acid.
Oh, moles.
We are titrating this against carbonate. So this is going to be HCl, nope, carbonate ion versus HCl, right? Y versus X. So this is, what do we call this region here? This is a buffer region. And then we have this guy here.
Do you have two buffer regions?
Hang on. Step by step, buddy. And then see how this line is slanted? I'm going to do this. What do I get for a distance here? I can't read my ruler. I'm going to say 4.3. So half of 4 is 2, 1.15. So this right here is my equivalence point. I'm going to go across. Oh, I was so close to what I wanted it to be. I'm going to go down. This is my first equivalence point.
Will we get an actual graph of this printed on?
Yep. Yep.
My graph is there on.
Yep. So my first equivalence point sees me reacting carbonate ion with hydrochloric acid. The chloride is a what? It's a spectator ion, right? So I'm just simply removing the carbonate or the chloride ion. And I'm going to get HCO3 minus. That's my first equivalence point. Okay? Then we kept titrating and we saw this second bump. It's leveled off more. Here's my line. And halfway is 2.8 is 1.4. So go across. Did it come close? All right. This is my second equivalence point. Okay. Second equivalence. So now I'm starting off my titration with HCO3 with bicarbonate. I'm adding more acid to it. And I get what, Declan? H2CO3. So here I start out with carbonate. By the time I hit here, I have bicarbonate. And by the time I hit here, I have carbonic acid. Okay?
Is that a 2 minus on
Carbonate?
carbonate?
Yep.
So
So we said that was a buffer region. What about this tailing off after my first equivalence point? That is another buffer region.
which your last name would not be.
No, what would it be?
It would be your
It is. This is my final pH here, right? And it's going to be mostly HCl at that point. This is right here is the equivalence point. This is the last one that we can have because there's only two hydrogens.
what is that?
This?
Yeah.
The final pH. It's not going to change. Now we're mostly acid at this point. Okay? Carbonic acid, hydrochloric acid. Okay, what is my sample type then?
Your sample type?
Yeah, what's in my Erlenmeyer flask? A weak base. What is my titrant type? What is my indicator that I'm going to use, do you think? Well, we're starting out high, and we got two regions. We got 9, and we've got 3 point.
There is one indicator that has 2 different.
Okay, one indicator. Does it work? We need to flip at 9 and 3.5. Okay, let's go with thymal blue. So for which pH range, Sydney? Okay, so we use thymal blue or phenolphthalein, Sydney said, for the first one. What about the second one? What would we use? Yeah, because when we look on here, Declan, even these doubled up ones here, we miss in thymal blue, we miss the second equivalence point because it's at 3.5. So we miss it. Your orange 4.
Oh, yeah.
No, because we need it at 3.5.
What am I looking at? Oh,
Methyl orange. Yeah.
because, yeah, sorry, that's what I meant. I saw the 3.2 and I just looked at orange.
Oh. We could also use bromocresol green.
Why?
Because it's,
3.2.
well, on ours, it's 3.5. In the notes, where they used actual graph paper, it's 4. So, yes, we would use methyl orange. Whoops. And that would be at the second equivalence point. Okay? Oh, what did I do? I put them in the wrong box. I skipped a box. These go in here. Thymol blue and methyl orange go in the indicator selection. I missed the equivalence point. The equivalence point, the first one was roughly 9. And the second one was roughly, let's say, 3.5. On my diagram, if you look on the notes, it says 8.5 and 4. But it's just how I drew my graph. Doesn't mean that notes are wrong. It's just how I do my graph.
On the diploma,
It'll be gridded out.
it'll be an exact number.
Yeah. Yeah. Okay. Indicators would be thymol blue for one and methyl orange for the second one. What's my buffer region? From 13
13 to 11.
to, okay, 11.5-ish. And then the second buffer region is 6-ish to 5.5. Does that sound about right? Yeah. Okay, perfect. And so ends the very last lesson of your high school chemistry career. Fun.